Hello, my name is Lotte Felius, and currently I am a second-year PhD student at CWI in database architectures in Amsterdam, the Netherlands. I was a former intern in Citus in 2022, and a part of this talk will actually address a part of the work that I did as an intern in Citus. Mind you, I was completely new into databases. I never heard about PostgreSQL, and I barely knew anything about any software engineering practices. So if you are also a beginner, please stay tuned for this talk because it might be interesting for you. And before we begin, this talk is lessons learned from benchmarking and profiling distributed PostgreSQL. It's not exactly about the benchmarking numbers that I got, but it's more about how I used the benchmarks to, in the end, identify some limitations or bottlenecks in Citus. So hang on and let's start. So this is the outline of the presentation. First, I'm going to tell a bit about different architectures that are used for different PostgreSQL offerings. Then I will talk about the goals for the research and the challenges that I faced. Then I will talk about how I actually benchmark Citus, which benchmark tooling I used, for example, and how I did it. Then I will talk about how I measured and quantified the performance. Following, I will explain how I identified the bottlenecks. And last but not least, I have some key takeaways for you that might help you if you also are going to profile or benchmark Citus or any other distributed PostgreSQL offering. So first of all, there exist multiple different PostgreSQL offerings, such as Yugabyte, Amazon Aurora, Google Spanner, CockroachDB, and AlloyDB. But there's also, of course, Citus. And these systems have in common that most of them are based on a shared nothing architecture or a shared disk architecture. And Citus is even a little bit different because Citus is an extension on PostgreSQL, which makes it easy to be compatible with the PostgreSQL open source ecosystem and libraries. And this, for example, is very handy whenever a new PostgreSQL version is updated, and it costs very little effort to make Citus compatible with this newer PostgreSQL version. So now we're going to explain shared nothing versus shared disk. So what is the difference between these two? Well, Citus is based on a shared nothing architecture. A shared nothing architecture basically is a cluster that consists of different nodes, but each node is considered as a separate machine. So each node has their own memory and each node has their own disk. And there's no way that each node can directly access the memory or the disk of another node. So how does that translate in Citus? Well, a Citus cluster consists of independent machines or nodes. The coordination between these nodes is actually happening on the software layer. And in the case of Citus, Citus manages the coordination itself. How does it do that? It creates distributed tables and shards across many nodes. And Citus also enables elasticity to scale up or to scale down. So whenever the workload intensity changes, a user can add nodes or remove nodes of the Citus cluster to match the workload intensity, basically. And for example, if we take Amazon Aurora, it makes use of shared disk. What is the main difference between shared nothing and shared disk is that it disaggregates compute and storage. So there are still separate nodes in the cluster, but each node are accessing all the same disk through the network. So this has some advantages because by disaggregating compute and storage, you can manage, for example, writes asynchronously. On top of that, Aurora has some smart tricks to minimize I/O, for example, because it only writes redo logs to storage, which basically means that it only writes changes of data pages to storage instead of that it writes whole new pages. Then it pushes these changes to the storage layer, and the storage layer itself takes care of finally writing the new data pages. So in the end, an instance in Aurora can just request the newest version of a page from disk. A downside, however, is that there's only one primary instance in Aurora, and there are multiple write replicas, up to 15, that you can configure. But this means, because there's only one write instance, that it can limit write throughput. And this is different in Citus. because when Citus 11 was released, the default mode of Citus enables every user to connect with any node within the cluster. And this means that the write throughput can actually be better because every node in a Citus cluster can take care of the coordination of a distributed query, but it can also serve the distributed query in itself. This, however, means that there are multiple connections established within the cluster as well. However, Citus, this is a smart trick. It caches connections to obtain a higher performance. However, a downside from this could be that this could lead to a connection scaling bottleneck in the end. But still, let's dive in. How does Citus do this coordination exactly? Well, let's go back to the PostgreSQL query processing pipeline. This consists of a parser, of an analyzer, of a rewriter, a planner, and an executor. The parser makes sure that the query gets parsed correctly, so it does also some syntactic analysis. And then subsequently, the analyzer analyzes the query and checks, for example, if the columns that are referred to, if they exist. And it also makes sure that the data types are inferred. Then we have the rewriter. The rewriter rewrites some query expressions into according to a set of rules, mostly based on relational algebra. And then the planner evaluates many different query plans and tries to choose the most optimal query plan so that the query gets executed most efficiently. And last but not least, we have the executor, and the executor makes sure that the query gets executed according to the query plan that the planner proposed. Citus extends the planner and executor phase of the PostgreSQL query processing pipeline, and this is necessary because a Citus cluster consists of multiple nodes, so it needs to have a different plan. And on top of that, it also extends the executor. The distributed executor makes sure that every query, which is now divided in query fragments, that all these fragments get executed on the right nodes. And also the executor is responsible for opening a connection from the shard to any worker node. So yeah, basically the executor is the final step. However, there are some potential pitfalls. The first is that PostgreSQL in general is process-based. This means that it's single-threaded in most of the cases. There are exceptions. But this means that if you want to fire multiple concurrent queries, you need to establish also multiple connections. And connections are not for free. Actually, they consume a bit of CPU, but they also consume a bit of memory. So it's not that you can have unlimited connections with any system. Also, within the Citus architecture, each connection to any node leads to one or multiple connections within the cluster because a query needs to be forwarded to a second node. This connection overhead, if there are a lot of connections, can increase ultimately the network latency because the network can get saturated by sending all the queries over to different nodes, but also the management of the connections can be pretty heavy. And on top of that, distributed queries require coordination. And this coordination is extra on top of just a single node system. And this coordination itself can just also incur a bit of overhead. So now the scope of our research. We're today benchmarking the scalability of Citus. And you can define scalability in multiple ways, but we are only adding nodes. We will see how much Citus scales by adding nodes, and we're also going to see how Citus scales by adding connections. This way, we hope we can identify some limitations or bottlenecks that occur in certain configurations. However, there are some main challenges, specifically for distributed systems like Citus. Because benchmarking a distributed system is not straightforward. It's actually pretty hard. And this is because nodes may fail at any moment in time. You have absolutely no control over that. You might figure that out very late. So that's really something you need to take into account. The second challenge is that monitoring all factors involved is very, very hard, because even monitoring a single node system already can be hard because there are many concurrent processes that are executed. at one node alone. So if you have multiple nodes, you need to monitor everything on all the different nodes. Plus, you need to monitor the communication between the nodes, such as also the network saturation and that kind of stuff. So it's also very hard in the end. How do we quantify this performance of a distributed system? Because there are so many factors. And another thing that we need to pay attention to is we need to avoid the Heisenberg effect. And the Heisenberg principle ascribes the uncertainty in the measurable quantities to the jolt-like disturbance triggered by the act of observation itself. Well, this actually seems a lot, but it basically means that if you monitor a lot of stuff, you might introduce noise yourself, that you're in the end measuring yourself. And the noise can also decrease the performance in the end. So to give a little example, if you will log every query in Postgres, this will incur a lot of overhead because you need to write all the logs also to storage, and this will have an impact on performance. So how did we benchmark Citus? For that, we use the Citus benchmark suite. It's available on GitHub. It already had a HammerDB and CH implementation. But we also added the YCSB benchmark suite. So now you can also benchmark Citus with YCSB. So what is YCSB? YCSB is the Yahoo Cloud Serving Benchmark. It's very often used. It consists of 7 core workloads, and the workloads are very simple. Just small create, read, update, and delete operations, also referred to as OLTP. And within YCSB, one record is pretty big. It's around 1 kilobyte, and it has 10 fields, and it consists of completely random data, as you can see. This is an example of a YCSB insert. You cannot make any sense of it at all. So YCSB is also compatible with the JDBC driver. This is very handy because the JDBC driver distributes the workload among many nodes in a Citus cluster. So we make a lot of use of that. And the performance of YCSB is measured in transactions per second. So in this talk, we are only focusing on workload A, which is 100% inserts, and workload C, which is a read-only workload, and it consists of 100% selects. We do this because we want to keep it relatively simple, but also because we want to measure as good as we can the pure effect of only inserts or only selects on Citus in this case. So this is the benchmarking setup. We have some kind of control plane locally on our laptop where it spins up the Citus benchmark repository. The benchmark repository spins up a driver VM, and the driver VM itself also spins up another instance of the benchmark repository, which in the end also initiates YCSB and the JDBC driver and actually starts the benchmarks automatically. So everything is done automatically. And the driver VM also makes sure that when the benchmarks are finished, that the benchmark results are collected and actually brought back to your local machine in the end. So here you see some results. These are for 100% inserts. And what we did here is we increased the amount of connections. We increased them until 3600 because after that we sometimes got out of memory errors, which means that connections cannot scale further than that if you don't want to get errors sometimes. But you can see that there is actually an increase in throughput in transactions per second. So the more connections you establish with the cluster, the higher the throughput is in case of inserts. However, if we look at the case of the 100% selects, we see different behavior because here with 800 connections, we see some kind of optimum. The throughput is the highest when we use 800 connections. And if we use more connections than 800, actually the performance starts to decrease quite a bit. And this is a bit odd behavior. So let's investigate why that actually happens. So how did we measure the performance? How did we further investigate it? What happened under the hood? For that, we use some profiling tools. Mind you that Azure itself also provides some statistics, but in this case, it was easier to manually use IOStat in this case. And IOStat collects like the CPU usage and the memory usage and I/O and stuff like that. Then we just use regular Postgres logging, but in a slightly different way, which I will explain later. And we use perf, and perf is between brackets because we only sometimes manually used it to identify under very large workloads which processes took up the most CPU. And this could only be done by hand as far as we managed. So I'm not going to explain more about that in this talk. And this is the profiling setup that we used. Actually, it's pretty much similar as the benchmark setup. The only difference here is that we also spin up a host process on the local machine, and this host process communicates with a server process that we spin up at the driver VM. They communicate with each other to give a signal, especially from the driver to the local machine, to give a signal when the cluster is configured and when the benchmarks itself are starting with YCSB. This is because the host process initiates IO stat on every node in the cluster to collect statistics, and we only wanted to collect statistics specifically when the benchmark was running to avoid very large logs of IO stat, and it's way more handy to only have the statistics from when the actual workload was executed. And this worked pretty well. Everything was automated, so it made it easy to analyze. For the sampling, this was a bit more complicated because we had to create a second user, which we call monitor, and this user was also executing a part of the workload. To be specific, 0.01% of the workload we had to find, and the workload we had to find was always 100 million records. We could do this because YCSB enables parallel execution. And the reason why we only logged a fraction is, like I said before, we don't want the Heisenberg effect. We don't want to increase the performance, decrease the performance. We had to do it this way because there was no feature yet that could log distributed queries. So to work around that, we made sure that we just logged a fraction by using a second user. So how did we identify the bottlenecks in the end? First, we looked at the research utilization, and to be specific, we looked at the CPU usage. And what you see here is a CPU usage of 100% insert workload. And what we can observe from this is that for all nodes, with 800 connections, the CPU usage is pretty low. It's around 20% with a peak in the beginning. And the peak in the beginning is probably because the establishment of connections takes always a while before everything is established. So that increases the CPU usage. But after that, it gets stabilized and it remains below. If we use 3,200 connections, the CPU usage is a bit more higher. But still, it's relatively low. It's around 40%, mostly even less. And also another thing that we notice is that the variation is a bit more if you use more connections. But that makes sense as well. Mind you, we used nodes with 128 gigabyte of RAM. So 100 million inserts fit in RAM. So we had no spilling to disk at all. And from the PostgreSQL logs, we, from the monitor user specifically, we tried to create some kind of profile of a query. And this consists of the time that a query spent on the worker node, or the child compute, as we called it. It's the blue bar with the dashes. And we had an overall execution time, and we also tried to kind of measure the latency. But what you can see of the insert query is actually that almost all time is spent on the child compute node, on the child compute. So this means that, a lot of the time, the query was basically waiting, because for inserts, everything gets written to a write-ahead log, and this write-ahead log needs to be flushed to disk, and there needs to be sent an acknowledgement back. And when the acknowledgement is sent back, the client gets informed that the query actually succeeded. However, if you have little nodes, there's probably kind of a queue for the buffers for the write-ahead lock, which makes it very slow. So adding multiple nodes helps a lot with increasing the average execution time. However, doesn't matter which configuration, always most of the time is spent waiting for disk I/O basically. So what do we conclude about that? Inserts seem memory limited. Clusters are mostly bound by the available memory, and there are around 31 connections per gigabyte. And we identified that disk I/O is a kind of straggler calls in this case. So now we look at the CPU usage of 100% select workload. We see here that the CPU usage is way higher. For 800 connections, it's already between 60 and 80, but for 3,200 connections, it's almost saturating the CPU. So this could indicate a bottleneck. And also here, if you look at the profile of a select query, you could see that it's very different. Actually, the compute itself on the worker node is very, very little, but the latency is longer, and the pink part of the bar actually indicates that most of the time is spent on the parent node, so the coordinator node basically. And this could be because the coordination is not inefficient. We don't know the exact cause, but there's room for improvement there. So to conclude, read workloads seem compute bound. If you use more than 800 connections in this case, this could lead to a performance regression. Note that it's only for the 100% read workload. And the system here behaves as compute bound. The reason is also probably because reads are very, very light, especially compared to inserts. And connections are relatively heavy. So most of the time is probably spent into context switches. So if you have a very light workload, such as only reads, then you need to take care of how many connections you actually establish to the cluster. So last but not least, the key takeaways. First, I learned to really scope your problem. Which benchmarking tools are you using? Which workload are you using? And which skill are you using? Because each different tool, workload, and skill may expose extremely different behavior, opposite behavior. So take into account what you measure and how you want to measure it. The second key takeaway is that benchmarking a distributed system can be very time-consuming because nodes indeed fill randomly at any time. And when you don't expect it, when you don't want it. So you need to take a lot of time. The third key takeaway is work step by step. So work really gradually. First set the scope, then micro benchmark, then identify anomalies or identify unexpected behavior or any other limitations. And then try to find the bottlenecks by profiling and also just thinking logically. The last takeaway I really want to stress is that identifying bottlenecks in a distributed PostgreSQL is hard because you almost never know the exact cause. And this is a general problem of distributed systems, I think, because even if you find some kind of straggler cause, it can depend on many, many different other causes. And if you remove one straggler cause, it will probably expose other bottlenecks, and you will forever be optimizing. But yeah, every bit helps, I would say. So this concludes the talk. Thanks a lot, and I really hope you enjoyed. And if you have any questions, feel free to ask them.